Good afternoon, everyone, and welcome to Ecology Live from the British Ecological Society. I'm Pete Manning of the Senckenberg Biodiversity and Climate Change Research Centre in Frankfurt in Germany, and I'm also the chair of the BES's Events Committee. I can't move to the next slide. Here we go, so that's better. So the BES is the biggest ecological society in Europe with 6,000 members in 120 countries. And we set up the Ecology Live series so that you can enjoy great talks during the lockdown period and hear the latest ecology even when you're working from home. So thanks a lot for joining today. We've got at least 650 people and they're coming into the room right now very rapidly. So there's been an enormous interest in the series, and I thank you all for joining. We have people joining from all over the world. Today, our speaker is Natalie Pettarelli. And before I hand over to her, I just want to say a few things about how to answer questions. There's a questions and answer box. If you put your questions in there, then we'll select a few questions to ask Natalie at the end of the session. We'll also collect up the questions and ask a few of them to Natalie, who will answer them on the YouTube video, which we're filming right now. And you can hopefully see more of the answers to her questions there. So with that, I'll hand over to Natalie, and she's going to talk about the application of remote sensing in ecology today. So thanks, and over to Natalie.
This has worked okay. So I'm Natalie Pettarelli. I'm a senior research fellow working at the Institute of Zoology at the Zoological Society of London. And today I decided to talk to you about two papers I did with Melis Lopez, who did a postdoc with me for 2 years. And we were really interested in the use of a time series for lawn cover mapping, and whether or not it's a good idea to do that and how it can improve ecology. To start with, I thought we could just go back to thinking about maps and why maps are important. I don't know about you, but I grew up with maps with my dad. When we were going on holiday, I was always the co-pilot, and the maps were the way to know where to go on holiday, where to choose which routes. So I really loved map from early on. And it's not just me, maps have been quintessential to advance human knowledge, support decision making, and this for thousands of years. Lawn cover maps are a type of maps that tell you about where you can find crops, lawns, grasslands, forests, lakes, any kind of class of physical coverage that we can find on Earth. And here is an early map for Australia, where you can see mostly was drawn by hand. Lawn cover maps are really important in ecology, and I know, and I would bet that many of you have used or will use lawn cover map, whether you do movement ecology and species distribution modeling to know what's the preferred habitat of your species or where are the corridors, whether you look at disturbance ecology and what's the impact of fire, or you are into ecosystem red listing and ecosystem dynamics, just knowing where ecosystems are or how their distribution changes over time. All of that requires lawn cover mapping. Lawn cover maps are also extensively used in conservation biology to support decision making, where to put a protected area, or for impact assessments, such as, is this a measure working? Is this protection working? Now, something that many do not wonder that much is how do we actually produce those lawn cover maps that we all use, or many of us use. So nowadays, we don't really draw lawn cover maps by hand, such as the previous example in Australia. We primarily rely on satellite imagery. And the process in most situations consists in taking one satellite image and then combine it with some field data. Make sure that you pre-process the satellite image to remove any kind of terrain correction or cloud. and then bring this information together to do some automatic mapping of lawn cover. You can do that in an unsupervised way by kind of clustering the information that looks the same and creating a class based on that. Or do a supervised classification, which is what you do when you're using field data. And in that situation, you decide how many lawn cover classes there should be in your satellite imagery. And then that automatic mapping is generally validated by using external independent information, either from on the ground or from other source of very high resolution satellite imagery. But what about those satellite images? Where do satellite images come from? One thing that sometimes is not very well appreciated is that there's a lot of different type of satellite that capture information in that electromagnetic spectrum that you can see on the top of that slide. And so two types of sensors are generally distinguished: the passive sensors and the active sensors. Now, the passive sensors basically capture the amount of light that has been emitted by the sun, went on Earth, and then got reflected back to space. So it relies on the sun as a primary source of energy to inform ultimately those lawn cover classification. Those active sensors, on the contrary, they basically send a beam of energy from space, from the satellite, and then they capture what comes back. And the information about lawn cover is derived from the difference between what has been emitted and what's come back. Within the passive sensors, there's generally a distinction made between the multispectral and the hyperspectral. Multispectral being those sensors that capture information in relatively broad band of the electromagnetic spectrum. So big green, red, blue band. While the hyperspectral really capture information in quite a lot of those very narrow bands. There's also a distinction, or sometimes people talk about optical imagery. Optical imagery being images that have been captured within the visible and in the infrared part of the electromagnetic spectrum. And then in active sensor, the two main type of sensors that people have heard about are the radar and the LiDAR. So radar is an active sensor that use microwaves. So it sends a microwaves beam, capture what comes back, and derive information about lawn cover based on the difference between the two. And while LiDAR use a laser. What's interesting here is, and is important to remember for later on, is that those multispectral sensors, those passive multispectral sensors that are very known are Landsat and Sentinel-2, and they can be contaminated by cloud. So if there's a cloud between the sensor and whatever you're trying to take a picture of, what you're going to see is a cloud. On the contrary, if you look at active sensor and radar in particular, so famous satellites or sensors that are radar based, or for example, Pulsar or Sentinel-1, those ones are not affected by cloud, so they can see through cloud. So most of the information that we use to do lawn cover are from passive sensors, multispectral type of sensors, so either Landsat and Sentinel-2. And recently, there's been more and more information coming from radar sensors, particularly with Sentinel-1. And so what's interesting is that there's been a lot of change recently as to what's available to lawn cover mappers and ecologists when it comes to satellite remote sensing. First, since 2014, there's been a huge increase in the availability of free imagery that combine both high spatial resolution, so 10 meters or so, and high temporal resolution with up to 30 pictures per year. And that's through the Copernicus program, which basically covers the Sentinel-1 and 2 satellites. And that has increased the opportunity to use seasonal variation to inform lawn cover mapping. At the same time, there's also been the ability to get co-registered information in the optical and radar domain. So that means images that are taking in the same place, so that the spatial co-registration is very easy, has been boosted because of Sentinel-1 and 2. which basically facilitate that course registration. And that means that it's much more easy to use both information from radar and from the multispectral, the Sentinel-2, together to inform land cover mapping. And that again could potentially mean an increased opportunity to combine information from different sensors to do better maps. And then on top of that, there has been some progress in techniques and algorithms to process satellite remote sensing images. So all of this together mean that potentially there's quite a good opportunity to access and produce better land cover maps by using all this new technology and all this new information. Now, you may say it's not because something is there that it's a good idea to do it. And so the question is it really a good idea to combine all this information, to use all the information to make better maps? What's the rationale to think that it could indeed make better maps? Well, the first is that the information captured by those Sentinel-2, those optical passive sensors, and the information captured by radar sensors is completely different. Because one tells you something about the color, while the other one is much more about the 3D structure. So this means that fundamentally this information is complementary. So putting them together could really give some good ground for improving your land cover classification. The second thing is that most land cover classes have different annual temporal signature. There's a lot of differences in how a savanna look like in the dry season and in the wet season. So getting information about those temporal variation within a year to inform your land cover classification could mean that you get better at detecting those land cover classes that are characterized by those annual variations. And then the third thing is that we do work in a lot, or at least anyone that works in a conservation hotspot tend to work in area that are affected by clouds. And so for the moment, a lot of the land cover maps are only using the optical passive information, which means that they get the problem of having to deal by cloud. And so combining with radar and taking into account all this huge information in the temporal domain means that you could get better at dealing with clouds. But all of that, you may say, sounds quite complicated, and it looks like there's a lot of things to do. So is it really worth? To which extent is it worth? And that's the question that we started to ask with Melis in two different settings. So the first one was thanks to a collaboration with Jane Hill in York, who had a project in Jambi, Sumatra, and was really interested in mapping peatlands. And we used that study case to look at what's the cost and benefits associated with trying to map land cover in the whole of the Jambi region using more or less complex approaches. So the site, which is in Indonesia on Sumatra, is characterized primarily by a relatively low level of seasonality, but a lot of cloud. And so what we did there was to try to map land cover in the region by comparing what was happening, whether we use only Sentinel-1, so radar information, or Sentinel-2, so multispectral passive information with 10 bands, while focusing on our ability to map peatlands to inform Jane's project. And then the other thing that we did was to try to see whether there was any benefits in using a multi-temporal approach, so using all the available information for a given year in the radar and in the optical domain, versus using a monotemporal approach, but basically a temporal average for the year we were considering, which was 2017. And then compare those monotemporal and multitemporal approach with the fusion of both either monotemporal or multitemporal approach. So what we did more specifically looked like I spend time trying to explain. But what's really important is that that you can recognize the steps I was mentioning early on, which is we had a pre-processing step to try to deal with atmospheric correction, terrain correction. Then we had a classification step, which is basically interpreting the information captured by pixels in satellite images and to map that so that you know which pixel belongs to which land cover. Then produce a land cover map and then validate, which is the last step that the land cover map produce. So the area we were considering had 1.5 million pixels. And we had to create, using very high resolution imagery, independent imagery, reference data that ultimately covered 1.2% of the study area. And the classifier we used in this example, so the algorithm we used to classify pixel, was a random forest. So what did we find? The first thing we found was that when you use the full information of the time series, when you use all the images, you get a significantly higher classification accuracy. And that's particularly true for radar, with plus 14-something% improvement. Also true for Sentinel-2, so the optical passive multispectral. And also for the fusion of both, the combination of both Sentinel-1 and Sentinel-2. So in all cases, in this example, it was a good idea to use the time series as opposed to just use monotemporal information. What in this situation also, we had better accuracies when we combined the information by Sentinel-1 and Sentinel-2 time series, as opposed to just using one type of information. So both using time series and using fusion resulted in better maps, more accurate maps. So, and that was particularly true for some land cover categories. So here is a table that gives you the user accuracy and the producer accuracy for each land cover that we considered, which is forest, water, urban, palm, acacia, fern, bear, and mangrove. And it compared those accuracy for Sentinel-1 monotemporal, Sentinel-1 time series, Sentinel-2 monotemporal, Sentinel-2 time series, and then Sentinel-1 and 2 monotemporal on fusion, or the fusion of the time series. And there's two possibility for the fusion of the time series, because in one case we did a bit of sorcery to account for the cloud to slightly improve the accuracy. And what you can see is that in general, using the time series was a really good idea. It was also interesting to see that most land cover classes reached their highest accuracy when combining Sentinel-1 and Sentinel-2 time series. So this was an example in Sumatra, not that much seasonality, lots of clouds. And we thought, well, what happens if you go into the opposite type of situation where there's not that much cloud, but there's quite some seasonality. There's land cover classes that are really difficult to separate. So here is a second example in the Penjeri National Park in Benin. The situation here is that there's a project going on with a number of partners, but primarily also Sarah Durant, where we have been looking at wildlife and the ecosystem as a whole using various approaches. But one thing that we were particularly interested was to try to see whether we could get better at mapping savannas. Because the map we had access when we started the project was basically making the difference between woodland and savanna. And there wasn't really much variability in the type of savanna. Well, if you go on the ground, you can really see something that looks more like a grass savanna, where you have no shrubs or tree at all, a shrub savanna, a tree savanna, and a woodland savanna. And you have a picture of the four of them. And the maps that were available at that point were mixing all those four categories into one. So we wanted to see whether we could develop an approach that would get better at mapping the cover of those different land cover type of savannas. So the Penjerey National Park is a protected area of around 3,000 square kilometers. And for the rest, the fact that it's seasonal and low level of cloud coverage have been introducing. So here, what we were trying to do was the same as before. Is it worth getting complicated? But we became even more obsessed to try to see what was the benefit of getting hyper complex versus just a little bit more complex versus not complex at all. So here we compared the benefits and the cost of having just one image versus a few images versus the whole time series. And we also looked at the benefits of adding bands. So if you think about Sentinel-2, it captures information in a number of bands. And to do your classification, you can use some of the bands or all of the bands. And we were trying to see, and of course that has a computational time cost. So we're trying to see what's the benefits of considering all of them versus just some of them. So here what we did was again play with Sentinel-1 and 2. And while really focusing on our ability to map the different type of savanna. And we compared monotemporal, which was 1 day, versus multitemporal, which is 6 images per year, versus hypertemporal, which is more than 30 images per year, informing the land cover classification. We also compare the combination of Sentinel-1 and 2 using a monotemporal, multitemporal, or hypertemporal approach. And finally, we compared what was happening when we were using just 4 bands out of the 10 plus monitor, the number of bands monitored by Sentinel-2 versus 4 band and the NDVI, which is the normalized difference vegetation index, tells you something about the greenness, versus considering 10 bands for Sentinel-2. So again, here is a schematic version of what we did. Again, you can see that it mostly consists in doing some pre-processing, classification, validation, and then some comparison using here with Cox and text. What we did in terms of timing, we considered all the images from February 2018 to February 2019. And we used, to inform our validation, but also our classification, we used ground truthing data that was collected in a national park in January 2019, plus some additional information derived from Google Earth. So what did we find? Again, we found that time series were really improving your ability to map land cover. Actually, the combination of Sentinel-1 and 2 time series performed as well as the time series of Sentinel-2 alone in terms of classification accuracy. What was interesting, however, is that fusing or combining Sentinel-1 and 2 led to qualitatively better maps, so the neater maps. What's for sure is that the use of dense optical time series, so that hypertemporal more than 30 image, significantly improved the classification outcome as to compare to using only a few image or 1 image a year. We also found that different land cover type were helped differently, or the accuracy changed differently, depending on whether you were using a combination of approach or not, so combining Sentinel-1 or 2, or just choosing 1 band, 4 band or 10 band, or 1 image, 6 image, or 43 image. So here you have a representation of the accuracy for each of the land cover type considered. For Sentinel-2, 4 bands, whether it's 1 image, 6 image, or 43 image, or Sentinel-2 10 band, whether it's 1 image, 6 image, or 43 image. And so what's interesting here is first to see that whatever the method you're using, mapping shrub savanna was quite difficult, and it wasn't really accurate. Fusion, so combining radar and Sentinel-2 particularly helped with grass savanna and tree savanna mapping, around 4% gain in accuracy. And time series had a particularly high impact for some land cover types, particularly the temporary wetlands, as you can see, which went from something around an F of 20 for something to up to 80 for something. So the more temporally variable, the more your time series is helping. So what's the key message from that presentation? The absolutely most important one is you should always wonder how the things we use, whether they are maps, algorithm, or data, how have they been made? How have they been collected? Because that tells you something as to whether you're using the best product or the best approach for what you're doing. If we look at this particular situation about time series and fusion, what we can say is that it's mostly always a good idea to use a time series, the optical one, to improve the accuracy of your land cover map. And the more images, the better. However, using more bands doesn't always mean better classification outcomes. Well, that's particularly interesting when you're thinking of about your computation time. Going from 4 bands to 10 bands didn't really make an enormous difference in your ability to map your land cover types. On the contrary, combining radar and optical time series is generally a good idea, although not systematically and depending on the relative importance of temporal variation versus 3D spectrum. The other thing to remember, or that I think this work shows, is that yes, we did something that was a bit more complex than just classifying one image. But when you think about it, the approach actually saved time, because there was no manual compositing to try to remove the clouds, particularly when we were working in Jumbly. And it was therefore much less sensitive to human errors. Also, those advances that we've been discussing are really accessible right now. All of what we did was done on free software and with free data. And to conclude, I would say that our work clearly demonstrates that doing those efforts and to go beyond the classical approaches did pay off for us, and ended up getting us access much better information about land cover type. So that's it for me. If you want to read more about those 2 papers that have been published this year in Remote Sensing in Ecology and Conservation and Methods in Ecology and Evolution. And if this talk was terrible, there's even a little video which is much more, which explain in a much more friendly manner what we've been doing. Thank you.
Thank you. Thanks. I'm not sure if you can see me. My video for some reason is not coming on, but I will switch, and we'll switch to questions now. It seems that my video is not going to show me, so I'm just going to have to hear me instead. I'm going to start with a very general question, which is, how do you determine the accuracy of your remote sensed land cover maps?
So you'll need some independent information, so information you haven't used to classify your satellite image. So extra information, and then basically you're looking at whether your map correctly identify area that you know are either mangrove, savannas, forest, etc. So you'll need some independent information to validate them. And then you look at the coherence between what your map tells you and what your independent information tells you.
Thank you. Yeah. And another question would be, what are the risks in using this type of remote sensed map to guide environmental decision making? Is it safe to do so, or is the uncertainty high?
Well, there is always uncertainty with doing anything, but better maps that are more accurate reduce that risk. And so that presentation showed that the more information you use, especially given the information available right now, the more you can reduce that uncertainty. And so therefore you're less likely to derive wrong conclusion from that land cover map.
Thanks a lot. So we have a number of questions of people asking, is it possible to do this type of remote sensing over water, for example, to monitor productivity?
So yes, so there is a number of products that allow you to look at the variation in sea productivity, but that comes from the information on the very top layer of the water surface, and so all the organisms that are primary producer, you can estimate the primary productivity using satellite information, but you can't go below that. So satellites do not see underwater. They only see what's happening as the top layer of the surface in terms of primary productivity.
Thanks a lot. And then again, another question which has come up as a recurring theme is what free software and what free data sets at the global level are available to do this type of work?
So we did a lot of it in R. All the Sentinel-1 and Sentinel-2 are free of access from the Copernicus program. There is also a number of other algorithms, some of which we cite in those papers, that are free of access. So it depends a bit. There's a number of approach that you can do, but a lot of them now are available for free, so open access and open source. But you can do it in R or on Google Engine. Okay,
so with that, I think our half-hour time slot is up. I'd just like to finish by thanking you for the great talk, this brilliant insight into the application of remote sensing in ecology. So thanks again. I hope you enjoyed it as well, everyone that's with us. Our next talk next week is by Thomas Crowther from ETH Zurich, who's going to be talking about whether trade-offs in functional traits help us to understand global biogeochemistry. If you're interested in seeing today's talk again, then have a look. We'll be posting the video up on YouTube, and we'll also be addressing more of your questions. There was just way too many to possibly answer them all in this short session, but Natalie will be addressing some of your questions in the responses to the YouTube video. So with that, thanks again for joining us, and hope to see you all again next week. Thanks. Goodbye.